Hello, everybody. How you doing? Great to be back. Joining you from Costa Rica at the moment. Got the rest of the team from all over the place. And for those of you who are new to the channel, we do this weekly, now Thursday, live stream to sort of track the progress and thinking that we're making for the Epiphyte project. And I will go ahead and drop in the comments right now a little brochure for that, which has links to our oh, here's Charles, great, that has links to our GitHub, some really helpful videos, great sort of backgrounders on the things that we're trying to solve for this summer before we build our next unit. And today, really thrilled to have a great group of regulars here, and also Kirsch from Clarity Technologies, who I'm going to have introduce him in a second. But Kirsch is part of an awesome DAC startup based in LA that I was lucky enough a couple weeks ago to drop in on when I was in town into their lab. And just within probably about 45 minutes, Kirsch, you remember I had so many questions, but my mind was kind of being blown by how some of the things you guys are doing line up with some of the things that we're trying to solve for, both on the chemistry side and even on the hardware side. So are we back? Okay, great. Can you guys hear me okay? Okay, great. Kirsch actually was really helpful for the SB 308 bill that we're trying to pass in California. It's the biggest carbon removal support policy in the world, or most important one, I guess we could say. And Kirsch led a team of constituents on a really important call with a really important assembly member. And that's how we met. And then when we talked a little bit more, I was like, oh, this guy's also kind of a genius on the chemistry side. And again, I found out more about his technology and what they're doing. So Kirsch, would love it if you could just introduce yourself and tell us a little bit about Clarity Tech, which I'll drop the link for the website here as well.
Sure. Thanks, Chris. Very kind introduction. And I'm sorry if it's quite loud in the back. We are actively building the parts of our sort of pilot plant right now. Can you still hear me okay, or should I move to a different room?
Maybe if you could just speak a little louder, we can hear you. It's just a little quiet, but it's certainly serviceable.
Okay, I will try to talk a little louder. So yes, so my name is Kirsch. I'm the head of science at Clarity Technology down in Culver City in California. It's a pleasure to be here with you guys. And I am very excited to hear more about Epiphyte. Just to give you a little bit of context on what we are up to here. We are basically a technology company that's developing a new DAC sorbent and process. And specifically, our DAC sorbent is something we came across sort of doing some research across a very broad range of different sorbent options. It's actually a low-cost, off-the-shelf sorbent that's very abundant. It's an alkali carbonate. We did some of our own sort of testing and material characterization work to sort of figure out how good it was and under what conditions. And we think it might be one of the best sorbents for arid climates. And our process actually also co-generates water, which can be useful as a benefit for water-stressed communities in arid climates. So we're currently a team of 8 people. So just a merry band of misfits over here. And we are actually designing and building, as you can hear, our first commercial plant that we're going to locate in Las Vegas, Nevada. And that's going to remove 100 tons of CO2 per year as a starting phase. And that's going to be sort of the first phase of a larger project that's aiming to remove 2,500 tons of CO2 per year and store that CO2 via ex-situ mineralization. So I know, there's some questions around our sorbent and things like that. I'll maybe pause here as far as introductions go, and happy to answer questions about our sorbent and whether there's any learnings we have that we can share with Epiphyte as well.
Yeah, that's great. And we'll get into that in 1 second. We have a few things that we want to kind of run by you, Kirsch. But before we do that, I'd love the rest of the team to very quickly introduce themselves. You got some of the key drivers of the Epiphyte project for the last year. And I'm just going to go ahead and start with David. Oh, I think you're on mute, David.
Sorry, David Wilson. I've been involved with OpenAir projects for about, I guess, 3 years now, and did some of the hands-on building and testing of the first Epiphyte, mainly on the electronics and the programming.
Excellent. Ling.
Hi, my name is Ling Kong. Yeah, I go by Ling. I am a biomedical engineer. I've been with OpenAir for about 2 years, a little bit more than that. And I'm located in the Bay Area, California. And so because Epiphyte, the device, the first go was in Pennsylvania, I am not able to physically participate, so I do remote design work for it. Yeah, I think that's all there is to say about me. I usually work on like mechanical stuff, less chemistry.
Cool.
You know, I'll just say that even though remote, Ling has made some great contributions with ideas and mechanical support, and even sent us some boxes that she built to help mount some of our sensors.
Yeah, and the real her and Christina and Ling's sister Janine have really gotten our GitHub repo into a sensible working order, which was very labor intensive. So hats off to Ling on multiple fronts. And then we got Seth.
Hey, I'm Seth Sternberg. I work professionally in software and product management. Been with OpenAir for a little over a year now, working exclusively on Epiphyte. And I'm also remote, based near Washington, D.C., and have been focusing mostly on the sensors and software.
Excellent. Then we got Jay.
Hi, I'm Jay Moriali. I'm an independent hardware developer consultant. I've been working with Dave and Ling and Chris for 2 or 3 years now, mostly on sensor, testing out sensors and stuff. And Ling and I and Edward were formed a team to do one of the OpenAir challenges, which we won. So very good folks to have on the team here. Been lots of fun.
Awesome. And then we have Charles, who's, I know internet is a bit shoddy, and he warned in advance that he might not be able to speak, but he can hear. Charles, are you able to say hi?
Hello, I'm Charles. Can you hear me?
Yes, we can.
Yeah.
All right. I'm a petroleum engineering student from University of Texas at Austin. I'm one of the team leads for our DAC team here. And we were hopefully discussing with Chris about building an Epiphyte model this year.
Yep, absolutely. Glad we can hear you, Charles. Yeah, and that's just for those tuning in here. I see 14 people are on the stream. As Ling mentioned, we built the first version of Epiphyte at the University of Pennsylvania in Philadelphia late last year. Based on that build, we're now trying to optimize and change certain things, make it function better. And the next build will be at UT Austin, where I am also located, hopefully starting in the beginning of this next semester. So it's great to have Charles here. And for those of you who are tuning in, as we talk through this is pretty casual, as you can tell. We sort of talk through issues that we're trying to solve for, bring in special guests. If you have ideas or thoughts, please do go ahead and pop them into the chat wherever you're viewing from, and we can pull those into the conversation. So that's great. So Kirsch, I showed you a couple things, but I think just to kind of start from the top here, I'm going to show this picture, which let me go off here. If you guys can see that is the system that David led the build of. That's currently still sitting in the chemical engineering department at UPenn. But you can see automatically it bears a certain family resemblance to the system that you guys actually built at Clarity Technology. And I don't know if just by looking at it, you could probably tell, but I didn't know, David, did you want to give just a a sort of a 30-second sort of talk through of what we're looking at here, just for Kirsch's benefit?
Well, the air comes in from the left, drawn by that fan that's on the right on the output end. And we've got a panel in the wide part, the big square part in the middle there. Although the part that has sorbent in it is only 8 inches square. And that was to save material. It's got, and it's got heating wires on both sides of the sorbent that heat it up from the sides. So we can blow air through and absorb the CO2 and then stop the air and heat it up and release the CO2.
Yeah. And at this point, thanks, David. We were kind of on the verge of maybe taking a pretty hard pivot around the fundamental design here. We have another member, Alex, who may or may not join, who developed a really miniature thing that he's calling Epiphyte Junior, which just had a PVC pipe that had no sort of, bulbous kind of chamber there in the middle from HVAC equipment. But when I walked into your lab and I saw a fancy version of what I'm looking at here, I felt encouraged that we were kind of on the right track here. So didn't know, just looking at what you're looking at right now, could you tell us a little bit about your DAC testing system? And if you have any questions about what you're looking at, maybe that would be a good place to start before we get into chemistry issues specifically.
Yeah, sure. Essentially, we have test systems at a few different scales. One is kind of on what we call our subscale or lab scale. So that is with these so-called ceramic core samples. It's basically a few grams of sorbent. And then we have a larger scale, what we call our brick scale. I can show you one of these actually. So it looks like this. So these are honeycomb monoliths. They have structured channels. And so that is a slightly larger scale. It's got like 600 grams of sorbent. And then the larger scale beyond that is what we call our 1 ton per year reactor. It is basically 16 of these bricks, and the Epiphyte system that you just showed looks a lot like that, but just a little bit smaller. The basics of your system when it comes to the fan are very similar. We have a fan, we have the duct. All that is pretty much identical. The way we sort of structure our sorbent and sort of coat our sorbent onto the sort of tip contactor surface is different. Since we have these ceramic honeycomb bricks, we basically coat those. We don't use pellets or particulates. And also the regeneration method we use is a little bit it's probably similar, but we don't use resistive heating to do sort of a direct heating of the sorbent. We use sort of forced air convection heating. So we basically heat up air. We close up the system. We have a heater inside the system. We can basically recirculate air and heat it up to flow through our channels and heat up our sorbent that way. The main reason is because we think that that's going to be a little bit easier to scale. We think that allows us to get sort of good heat transfer, not perfect, but good heat transfer into the actual sorbent that's coating the channel walls. There is a lot of interesting things that can be done with the sort of joule heating, resistive heating process that you guys are looking at. So I don't by any means say that that's, better or worse necessarily. That would be pretty much it. Yeah, David?
So it seems like effectively you're sacrificing the purity of the output. Do you have a spec on that or any kind of requirement?
Yeah, so the purity of our output is between 80 to 95% CO2, and that's because we control the void fraction of our reactor such that it's very small. And so as the CO2 desorbs, it ends up displacing a lot of the air inside the reactor. We ultimately recover 95% or so of the CO2 from our desorption process and maintain CO2 purities of 80% plus. We could then enrich it further if we wanted to with downstream processes like cryogenic distillation and such. Generally we haven't had major concern. That's primarily because of the low void fraction.
Great.
Can you just describe for dummies like me the low void fraction? Just define what that is.
Yeah, there's just not as much empty space inside the reactor. A lot of it is taken up, and so there's just not as much air in the reactor to sort of contaminate your CO2 stream.
Got you.
Now the length,
I did it.
the length of your honeycomb thing, so in the direction the air flows, did you optimize that to maximize the CO2 capture and minimize the resistance, or is that something you've actually looked at?
That's a really great question. We did do some research around that. We, figured out what the effect of sort of a higher pressure drop versus higher CO2 capture fraction were at different lengths. Coincidentally, we found that 6 inches worked well for us in terms of the total depth. So that's coincidental and fortunate for us, because a standard sort of geometry for these honeycomb monoliths is a 6 by 6 by 6 inch cube. So this is roughly, get a sense of the dimensions here. That's what we're looking at for a reasonably optimal, not precisely optimal, but reasonably optimal depth.
Would that depend on the particular sorbent that you use?
Yeah, most likely.
Yeah, and you had mentioned too. Kirsch, when we spoke, and then we confirmed it with our LLM that the kind of sorbent we were looking. We did the zeolite originally, just because that was most available. We very quickly decided that wasn't optimal for reasons we've discussed at length around absorbing too much water, etc. And then we found Luatit was recommended to us. We did go ahead and buy that. That's at the lab in Philadelphia. But you had also, said that the process that you use, which has many advantages, that type of sorbent wouldn't be able to stand up to the heat that's required, I guess, for the calcining process. So you had recommended a couple of other families of sorbents like MOFs, etc. Right? So we probably want to go a different direction if we do go the ceramic brick option, right?
Yeah. So I think maybe if I take a quick step back here, it sounds to me like one of the goals of Epiphyte might be to try different sorbents or have a reactor that's compatible with multiple different sorbents. I think that one of the benefits of the structured honeycomb monolith we have is one that, coating this monolith requires a fairly similar process across a range of different sorbents. We can coat this with amines, for example, polymeric amines like PEI. It's a very common one. You can coat this with alkali carbonates. You can coat this with zeolites. There is a caveat, though, that generally speaking, the way that these are coated is basically you generate a solution of your sorbent, and then you dip these honeycomb ceramics into it. So if your sorbent is already quite hydrophobic, it will be challenging to generate that solution and coat a homogeneous coating on the surface of your channel. Luatit, it sounds to me, has a sort of organic sort of resin that it's composed of. And so I'm not too sure if that will dissolve in solution or not, which could be a constraint for this. Does that kind of address part of your question there, Chris?
Yeah, I mean, and we're totally open to going with something else. And there is a member of the UT team who is a postdoc, I think, in a chemical engineer, I believe. And he's looking at synthesizing MOFs. So we're willing to look at whatever sort of fits the spec to find, other options. When I was at your lab, you're in a little corner there where you're sitting right now, and you got some
office, yeah.
Sigma things hanging out over there. But we're looking at a baseline for the context in which these will be built, are probably mostly universities, maybe some sophisticated makerspaces. Could you just tell us a little bit about what it's like to go through the full process of coding a honeycomb like that to make it work? How sophisticated, safe, like what's required to do that?
Yeah, so I can tell you how I coat these generally. And I should say I typically coat samples that are on the lab scale. And so a lab scale sample looks like something like this. It's a core sample. This is probably more for the mini Epiphyte Junior. So for context, this is what how that scale looks in comparison. So basically, in either case, you can use a similar process, but obviously you need to scale up for the brick. So what that looks like is first, you get your ceramic, your honeycomb brick, or just your core sample. You generate a solution of your sorbent. Optionally, and I would recommend this, you actually have a wash coat. So this is like a high surface area particle that you coat on the surface of your honeycomb monolith first. The benefit of that is that it vastly increases the surface area that you have on your monolith. And then you can impregnate that what's called wash coat layer with your sorbent. And then you have very well dispersed sorbent, which is ideal. So to do that, basically, you generate a solution of your wash coat. And then you literally can dip your core sample or your brick into the solution. You immerse it for a little while, seconds. You take it out, you remove any excess solution that's still hanging around in the channels with, compressed air, for example. And then you take that brick or core sample and you dry it, you weigh it, you see how much you've loaded. If you want to load more, you can dip it again and again and again until you get to the desired loading. Then we have basically, if you have a wash coat, then you'll need to do what's called the calcination step. That basically is a very high temperature treatment to make sure that your wash coat adheres well. And then you'll add your sorbent. If you don't choose to use a wash coat, you can just add a sorbent and just dry it as you would normally, just in an oven at whatever temperature you want. And then you're done. So that's essentially it. It is a dip coating process. So that's as straightforward as it gets. This isn't how we would coat our bricks necessarily at a larger scale, but it works well for lab scale. And so we're able to, coat, 5 different combinations of wash coat and sorbent and different loadings per day on the lab scale fairly easily. And you don't need very much. So in the context of a university, I'm highly confident that the required equipment is already there. You would, of course, need to purchase the chemicals, but you just need beakers. You need like a magnetic stir plate that's sufficient for mixing your solution. You literally dip your core samples or bricks, and then you need a compressed air source. Most chemical labs have compressed air or nitrogen, and then you would need a lab oven. The only caveat is if you do need to calcine your brick, which you would if you wanted to add the wash coat layer, you'll need a furnace. So those furnaces are not as abundant, but most universities, you can find a furnace in most universities that can be used. So we just have basically a very standard, thermal Fisher furnace, and we calcine our bricks at 450 degrees Celsius for 4 hours before we do our sorbent impregnation step. So that's the entirety of the process.
Any questions, guys?
So you're using aqueous solutions?
Yes.
Have you considered that maybe with some sorbents you might have better results with another solution, different solvent, like, I don't know, ethanol or whatever?
Yeah, absolutely. Polymeric amines like PEI are typically dissolved in ethanol. So I will say this general protocol that I'm talking about has specific particular things you'd want to change for specific sorbents, but the overall process and the required chemicals are very modest.
And it sounds like you can do it kind of where you are without, like, in terms of safety and stuff like that, if there was a certain baseline of knowledge among an academic or someone who works in a lab, it sounds like it's not too big of a hurdle to potentially do that, provided we can get the furnace that could generate that level of heat, right?
Absolutely, yeah. It's not the process of coding itself that poses any environmental or human toxicity risk. It's the sorbent. So have to think about what might happen if your sorbent is your sorbent going to like produce any volatile compounds that are bad for you? But it's not the process itself that's the issue.
Mm. Okay. I just wanted to show a picture. Go ahead, Jay. Go ahead,
Chris,
Jay.
I apologize, everybody. I have an appointment to run to. Chris, it was nice meeting you, and I'll try to catch the rest of this on the recording. See you guys next time.
Great. Thanks, Jay.
Thanks, Jay.
Bye-bye.
Great. And Kirsch, we were kind of, if we were to stick with our again, just to show this image here, our original design or something like this. The other thing I'll just show you real quick that we were considering recently was that one of that miniature version I told you about before looks like this. And we already started to look at, well, what if we did something that was a much larger PVC that had that? But let's just assume for a second we stick with something more like the original design. We were just thinking very simply that a monolith brick or two bricks next to each other could either, one of the sort of long ones or one of the ones that are, more sort of narrow but wide, that we would just sort of position it in the middle of there like that. Is that kind of how yours sort of fits into your system?
Yep, very similar. We have silicone rubber around the monolith. We don't use it for heating. We just use it to, keep the brick secure. But that's it.
And for your heating system that you described, do you just sort of put it between the different, like where the fan is, like on either side of the monolith, so that the air is being heated up as it's coming in? I don't know if you could just give us a sense based on what you're looking about where the heating system that you use goes.
Yeah. So basically, this system here, imagine you close off. So there's a few different ways to do it. If you want to collect high purity CO2, you would close off both sides of the reactor. You could have a fan that basically recirculates air around the monolith, and then you would have a heater. Your heater could be above or below the monolith, and you would direct air towards the heater, and then it would basically heat up the air. That air would have to pass through the monolith and to recirculate through, and then get reheated by the heater. That's essentially the idea, is you have recirculation of air through a heater.
Okay.
The other way to do it, and I think this is simpler because it doesn't require you to close off the reactor. You don't have to worry, about sort of leaks of CO2 as the CO2 is building up, or like pressure being a little too high for the vessel, is basically continuously sort of desorbing the CO2 off the monolith. And the way you do that is basically you have the system as it is in this image. You have a fan, and then you basically blow air through a heater, and then that heater is directly upstream of the monolith. And then you blow the air right through the monolith. It heats up the monolith, it releases the CO2. That CO2 is now flowing out of the monolith to the other side, and then you have a CO2 sensor at the outlet. You can measure CO2. If you know your flow rate and you know your CO2 concentration at the inlet and the outlet, you can figure out how much CO2 is being desorbed.
What do you guys think of that, David and Seth and Ling?
Oh, that's pretty cool. So you never have a vacuum phase?
Yeah, we don't. The thing is, if you're going to use an amine, Limited sounds like it has amines decorating the surface. And so the one thing there is amines are sensitive to oxygen, as you probably know. So, I'm not too sure how the system currently works to sort of take into account the instability of amines. But, if you did use amines, you would probably need to either have a vacuum chamber, or you need to flow nitrogen, pure nitrogen through the reactor for desorption. in the test system.
And what do you think, Kirsch? We are open to whatever kind of sorbent that is safe and not exorbitantly expensive. Like you had mentioned a couple of families, MOFs, alkali carbonates, I think were one of them. I didn't know if you even thought of any kind of off-the-shelf sorbents that we might be able to look up on Sigma or other places that would definitely be a good fit for this application using a honeycomb monolith that would be relatively easy to implement.
Yeah, I think a standard go-to is usually polymeric amines, like PEI, and you can get that on Sigma. We have some sitting on the shelf here. There's a lot of different amines you can buy right from Sigma. You can dissolve it in ethanol, like David was talking about, and you can basically impregnate your monolith. You can also buy the wash coat. So I was talking about the wash coat earlier. The wash coat's very helpful. It increases the surface area of your monolith a lot, and it makes your amines much more productive because they're much more dispersed. They're not basically on top of each other, and that improves the kinetics a lot. So essentially, you can buy those things right off Sigma. You can buy alkali carbonates right off Sigma as well. They work great with this process.
And the monoliths themselves, I know you guys have those custom made to meet your very specific purposes, but you directed me towards just catalytic converter filters, which look exactly like the thing you had in your hand. So you thought we could basically find, and they're in every size, shape, circular. You think that would probably be good to go, at least kind of work in principle if we just ordered something off the shelf that fit the dimensions we need, right?
Yep. We started by buying all of our ceramics from China. There's a lot of very, decent monoliths you can get. A lot of different options there. You don't need anything fancy to get started.
Yeah. Guys, thoughts, questions?
Kind of a side question. Before I forget to ask, what CO2 sensors do you use?
Yeah, this is a really good one. We went through a lot of them. So I think that it very much depends on how much you're willing to pay. But I think the CO2 sensors that I'd recommend are probably from PP Systems. There's these SBA5 CO2 sensors that are great. So it's SBA/5, and then Lycor LI850s work well as well. Those would be the ones I'd recommend.
So do you have to take any special measures, say, to shield them from turbulence so you get a stable result?
No, we're doing all of our measurements in this case using basically we sample the reactor with a pump, and each of these sensors comes with a pump, and it'll flow in a target flow rate of the sort of fluid, and you measure CO2 that way. So we haven't had any particular needs to account for turbulence. The other thing is the SBA5 sensors. They do need to be sort of zeroed every periodically with sort of a CO2 free fluid, and so that is something you can do fairly easily. They have these like lime scrubbers that can scrub CO2 right out of the air, and it'll sample that gas every 20 or 30 minutes. So that's something to keep in mind. But besides that, there aren't any serious maintenance requirements for these.
The scrubber is built into their system?
Yeah.
For the brick that you showed, sorry, I dropped off for a second. For the brick that you showed before, Kirsch, you had mentioned, I think the one that I saw that was large that kind of looked like an older brother to Epiphyte. I think you said that was a 10 ton or 1 ton per year system. Is that right?
Yep. The 16 bricks are a 1 ton or few kilogram per day system.
Yeah. you had 10 bricks in there. I mean, I guess we'll have to look at it in terms of how our works. It's possible maybe we could get 4 bricks probably as a quad based on the size of it, but that's more than I would have thought given the size of it. We've never really thought about that, guys, very clearly. I don't think we knew how much carbon might be removed based on what we were building. We just first wanted to demonstrate that carbon was in fact being removed, but that's promising that it's that efficient and has that much sorbent packed into it. But we'll have to take a look.
Yeah. There's also, I can also share some links to some publicly available sort of presentations that were made to the DOE by some DAC companies where they show some of their own reactors. They look very similar to Epiphyte that also use honeycomb monoliths. That may be helpful here as well. But those, I think, were single brick reactors and also 2x2, kind of like what you're talking about, Chris, just four bricks there. And yeah, you can capture a lot with just 4.
Wow. Did you guys understand, David and Seth, the whole why we don't need a vacuum part? That would obviously be good news. Is it also possible, Kirsch, to add a vacuum to have any auxiliary benefit, or is this just the design that you have that it's not relevant?
Yeah, so the vacuum is most likely required if you're going to use an amine. The reason we don't need vacuum is because our sorbent is stable in the presence of air. That's a huge benefit.
Okay. Seth, I think you were about to say something and I cut you off.
Yeah, I was just going to ask how frequently you need to refresh either the wash coat or the sorbent bath.
So one of the good things about our sorbent is because it is stable in the presence of air and also stable thermally, it doesn't need to be replaced. The only thing that we've seen is that if, after, hundreds and hundreds of cycles, you need to replace it. It's most likely because you've, put too much compressive force on the surface of the core of the material, and so as the material absorbs, it starts to expand, and so that will start to create cracks in the material. So technically, we don't need to replace it because the sorbent itself is like a rock, literally. Yeah.
The other reason we might want to use a vacuum is I'm just thinking that you're pumping air in to heat the honeycomb, and you're already diluting the output. So what would be, say, the amount of CO2 in, say, moles or liters or whatever that could be released in one cycle compared to the amount of air that is required to heat it up?
So you mean on a per brick basis?
Sorry?
You mean on a per brick basis? How many moles CO2?
Yeah. For example, really it's just a ratio. However many bricks you have, you need to pump some air in, a certain amount of hot air to heat it up to the desired temperature, and then it'll start releasing CO2. How much CO2 can be released in one capture cycle, and how does that compare, regardless of how many bricks you have, with the amount of air that's required to heat it up?
Yeah, I would say on a molar basis, we're talking somewhere like 4-to-1 ratio of CO2 to air.
So that would mean a maximum purity of, roughly 80%, I guess.
Yeah. And it goes back, I think, also to how you control the void fraction. I think that's the critical parameter to consider there. You don't need to.
Sure.
It depends also on, does the desorption duration matter a lot? If the desorption duration matters a lot, then maybe you want to be heating up air to a higher temperature. Maybe you'd want a higher volume of air that's being heated up to the same temperature to transfer heat to the monolith at a more rapid rate, sacrificing CO2 purity as a result. But we've taken the opposite side of that trade-off.
Okay. Thank you.
In Kirsch, with your system, you guys are really using it to sort of test the efficacy of your sorbent. And so I would imagine the system you've built is a catch and release system. You're never capturing or storing any of the CO2 that comes out of it. Is that fair to say?
Generally speaking, that's true. We do have our own sort of storage process that we're working on as well.
Can you imagine a storage process that could be integrated into something as small as we're doing right now that is relatively easy to execute on? That's been sort of an open question for us. I've told you that we are exploring possible integrated mineralization,
Yeah.
but we're open to any kind of options where it would be cool to be able to store and do something with the carbon, even if it's in gaseous form.
Yeah, I mean, I think that would be very interesting. There are some details that have to be thought out, but like brucite's a very reactive magnesium hydroxide, very reactive. You can react it, at room temperature and pressure with CO2. Consider using something like that.
So would that be basically having a sort of a closed tank of some quantity of brucite that's sealed, that we just literally have our tube of CO2 coming off of the Epiphyte going directly into it? Something as simple as that?
It'd probably have to be a solution. And so you'd have a solution with brucite, and most of it would not be dissolved, so it looks pretty milky. You would flow CO2 through it, like you're saying. You might want to recirculate that CO2, make sure it all gets captured. But yeah, effectively.
And that's pretty quick in terms of the mineralization process with brucite under those conditions? Or?
Yeah, I would say brucite, when thinking about that on a larger scale, brucite is most likely not the best choice as a mineral for CO2 storage, because you actually have to often generate, often requires the production of CO2 to make brucite in the first place. But for the sake of, something on the lab scale, that would work fine, I think.
Yeah, that's what we're looking at this point. Just something to get us started. Other kind of questions or thoughts, including you, Kirsch? I don't know if you have questions about the project itself, but if this is a great opportunity for the gang here to pick Kirsch's brain on any aspect of what we're doing here.
Yeah, I mean, I'm curious. I think it's really exciting what you guys are doing. What do you guys think are the next steps? It sounds like you got this project at UPenn, and then you have some ideas for a smaller version, and then you have some ideas around potentially CO2 storage. What's next?
Well, one thing we definitely do want to, if we feel like we can adequately solve for some of the main problems that we faced with the first one, and we haven't even talked about all of them. So if there's other ones, guys, that you want to sort of share with Kirsch, that if we can feel like we can get to a good enough place where we want to try something again, we absolutely hope to hack the existing system we have at UPenn, but we also want to be able to create another system that we have more direct control over indefinitely. And because we have this amazing net team at UT that has already built a miniature DAC unit and is very game to do it and has the right facility, we do want to start building, get on track to start building in September another system that implements some of these changes, probably the monolith honeycomb, and we'll explore the heating options maybe a little bit more with you specifically. But guys, I don't know if there's anything else bigger picture that you wanted to share about what we're trying to solve for right now, or even the sort of future of the project. I can also add my thoughts, but I mean, I think a key thing that I shared with you, Kirsch, is that keeping it open. We built the first one, and it's not the one that we want to recommend yet that we get a bunch of other people to build, although we learned an enormous amount from it. And we want to get the first version, if you look at that as version sort of 0, the first version to be the one that we really start to promote the repo and to get other people to build it. And from the get-go, we've had an idea that can we try to get more and more teams that have the capability to build, and in a pretty regular timeline, once a quarter or something, we try to build one that adds another optimization that we're thinking about. So you could say, one of the things that Seth is really focused on is we want to be able to take the sensors for this and to be able to monitor in real time and display that on a website. And then any other new epiphytes that are built also reporting in real time and showing the world what we're doing, not just the amount of carbon, but are there positive outliers that we see that are doing better than other ones? Why is that? You know what I mean? And to keep everything as open as possible is really the idea. And then new ideas will come in as the community grows about, well, what do we want to do with it next? What's the next build going to try to focus on? And obviously the bigger the community and the more build capacity globally, the faster the rate of innovation will be. So that's the general idea that we have here. So we're at kind of a critical phase where we learned an enormous amount at UPenn, but how can we now move into the next build being something that's a bit more functional and replicable for a larger group of people? Then it's my job to try to recruit as many universities as possible to have teams and build these in parallel and keep building our audience and our community.
That sounds awesome. Yeah. I mean, one thing there that just came to mind is, if you had this like decentralized, network of epiphytes, all sampling very unique humidities, temperatures, things that really matter when it comes to performance of a material, then you could have a very interesting data set that's like an open source for a variety of different sorbents. Where you're trying something in very cold environments, tropical environments, etc. That kind of thing that companies spend a lot of time trying to control in their own test systems. Wouldn't it be great if like the next tech company could just leverage open source data sets to figure out what sorbent to use and things like that?
Bingo. Seth, you might even want to elaborate on that. That's kind of Seth's big data. If you want to even talk about what we do, it's very similar to what you've described in the past, Seth. So I don't know if you have anything to.
That's exactly the idea. Is we want to get this distributed system where we've got all these variables and different conditions, and there's enough crossover in there, so it's not every location is not using a different sorbent. You need to have multiple locations that are using the same sorbent with different environmental conditions, and you need to have the same environmental conditions with different sorbents and all these crossover variables. Now you've got a single data set that is available for the research community, is available for DAC companies, but also is just available on this website for anyone who wants to come and poke around and explore. Right? We want to have this front end portal to all this data, so that anyone can come and explore and figure things out and post to the community and suggest, new areas of exploration or new insights that they found.
Yeah.
That sounds awesome.
And you can imagine too, Kirsch, like so much of the public social acceptance around direct air capture, a lot of people have to sort of take it on faith from renderings and verbal descriptions. And so much of getting public acceptance is not just about, is it safe or is it not safe, but getting people excited. And can you have a sort of a charismatic object that you can literally roll out into different places in front of politicians or students or whatever. And so we do hope that this will have a life that's focused on innovation, but also can we use it to display what direct air capture is all about. And if you have people building it all over the world, we think that could be mobilized for that purpose. I'm an activist. I always sort of try to think about things in those terms. So that'll be, very, very exciting.
We'd love to take this. Right now, we're looking at university labs, our primary target. We'd love to be able to take it down the line to, public school projects and people in their garage, right? Just as a hobby project, right? Oh, I feel like I want to capture my own CO2, right? I know plenty of people that have bought kits to build, rooftop windmills.
Could I propose something then? So I don't know if this will work, but there is some literature around this. But like, what if you 3D print the whole thing?
Yeah.
You 3D print the contactor, meaning the monolith, as well. There's some zeolites that have been 3D printed into monoliths. Basically, these honeycomb structures. I think you can use fairly, simple 3D printers. You just need the right ink, so to speak.
What about the heat though on that part? I've been obsessed with the 3D printing and many immediate and then more crazy ideas around this project for a long time. But we do worry just about melting. You'd have to, I guess, pick a type of medium or print material for that can withstand these kind of temps. But
high temp resins for sure. And I think, like one of the challenges perhaps with the resistive heating method is, there may be a very large temperature gradient across your material. So your surface where you're heating this up is going to be a lot hotter and potentially much more likely to cause melting than if you were to sort of heat air or some other fluid that would then transfer heat to the monolith, because that air can be at like your target temperature, and you just effectively like transfer flow that air through a heater, a heating unit, and then into the system. And that whole part of it, the heater and everything down upstream of it, could be outside of your 3D printed contactor. Again, I'm not sure if this would work. There's obviously, you brought up like a valid point. So, but I think that kind of thing could help scale this up.
Yeah, I mean, UT, one of the things that's exciting about that is they have one of the top 5 ranked additive manufacturing departments and facilities in the country. And so they have a lot of capability, not just around your typical sort of, filaments and stuff, but other more novel materials for it. So it would be super cool to experiment with that. And Kirsch, we think it has value to DAC people all over the place. You know what I mean? For reasons that you said around research, but just creating a charismatic project that makes people fall in love with DAC, in a different kind of way. So please consider yourself part of the family here. If this is something that struck a chord with you, you have a lot of knowledge and experience. So it'd be awesome to have your help. And I see a couple of other people here. Semois has posted that she wants to get involved, which is awesome. Is a chemical engineer, it looks like. So Semois, I'm going to just pop in our Discord invite link there. Let me know in the chat if you can see that. If you come in, I'll keep an eye out for you, but I'm also going to give you my handle, which is also in the chat. So when you come in, you can DM me and we'll get you situated. We'll put you in the channel here that we talk about Epiphyte stuff with. We would love to have you involved, as well as J3 Anks. Anybody here who's finding this to be a cool project, it's all about participation. So please do join us in the discussion in the Discord for sure. So Semois, if you could just let me know if you see that. When I post it here, sometimes it posts to other channels. I want to make sure that you have it. All right, we're coming up to the hour. I felt like I had one other thing I wanted to ask, but I can't remember. Anybody else have any other sort of thoughts here? This is super helpful, Kirsch. I mean, really, it's. I think it's really put us. What do you guys think about the? Do we want to go with start assuming that the monolith approach is going to be what we want to go with? Because it looks like it's the kind of thing that we could put in there. I mean, I think the one thing, Kirsch, is we probably, the way that our system works right now is we pull out this metal chamber, which I think I showed you. If we use the monolith, we might want to size one that fits in with that existing one so we could just push it back in. I can even show you a picture. Or do you have like a hinge where you open up the part of the, let me just show a picture so I don't drive everybody crazy here. So if we're looking at this guy here, okay, you see that middle box here, we open that up and we pull something out that's quite thin. It's only like 4 inches, wide or 5 inches. And that's where that other sorbent chamber sat. I guess conceivably we could have a monolith maybe that is kind of shaped like that. I know those are offered. Or if we don't, we do something that's more like a square brick, we're going to have to change the design here where we probably have to open it up almost on a hinge so that we can insert the brick in. How do you put your bricks in your system that looks like this? Oh, I think you're on mute.
Yeah, so we have a grid of in a sort of metal frame, and then we have silicone seals around each square of the grid, and then we basically push the bricks in to each square. I think that the monolith in the system that you're showing here may be useful. I think that the pellets that you have now in the lattice sort of cartridge is also perfectly fine. I think the core samples are very helpful in particular. So I might suggest using core samples for your Epiphyte Junior as a way to get started. I think those are a lot easier to coat. That might be a good place to start.
Here's a thing that J3 Angst put in. I just want to put you, if you can see that question there, be careful of the trade-off between the surface area and the loading obtained from the coating process. Mm-hmm. Is that meaningful to you, Kirsch?
Yeah, I mean, I think that it is true that there is a trade-off. So it depends. The actual trade-off that I think is being referred to here is that you have a sort of reduced surface area in some sense because you have these open channels that aren't explicitly filled with sorbent. You have the sorbent coating the surface of your monolith as opposed to the pellets, which have this like spherical surface area. However, I would also say that the sorbent that is exposed to the air is very significant. So the actual, exposed surface and the kinetics of the adsorption process can benefit a lot from just coating a thin layer of that sorbent on the surface of a material, as opposed to having pellets where the adsorption of CO2 deeper into the pores of the pellet are going to be rather slow. On the other hand, you can also load a lot of sorbent, but you can't load too much, right? If you load too much, you end up clogging the channels, which is also suboptimal. So there are a few trade-offs here. There's an art to it for sure.
Can I just say one other thing before we jump off that David could speak to, just if we take one extra minute, is that the reason why we got to replace, this guy here is because of the airflow. It just was too packed in there, and we didn't even know. We just poured it in there and did this. So we're very attracted to the honeycomb monolith thing. So there's a very practical kind of terminal reason, I think, why we have to move beyond this, just from getting better airflow in. David, did you want to add anything to that at all? I mean, I think we feel like we have to move on from this approach for the reason I just stated, but if there's any other details you want to share.
To me, the biggest reason to move on from that approach is just the difficulty of putting in the sorbent and removing and switching out a different kind. You have to disassemble the entire thing, and we've never even done that before. We just built it once, and it's not very user friendly.
It also replaces the one truly custom part in the whole system.
The heating system, you mean?
No, the sorbent panel, right? If we replace that with just an off-the-shelf monolith.
And just Ling had mentioned this a while ago when I first showed it. It's just something that just props it up, so it's just right there, evenly placed within the larger chamber. It seems like just an incredibly simple set of parts to be able to get that brick in there to do what it's supposed to do, if I understand you correctly. But I know we're at time here. This was fantastic. Charles, I know you weren't in the best listening or viewing situation, but hopefully all this made sense. It's recorded. It's on our YouTube channel. But let's you and me and the other members sort of talk about questions that you have as we look to rebuilding this in Austin. But everybody, thank you guys so much for joining. J3 Angst, awesome ideas that you shared with us. We didn't get to all of them. One was about microwave heating. I'd love to pick your brain on that. And Semois, along with J3 Angst, hopefully you guys will join us in the Discord and meet the team live. We'd love to have your involvement. Kirsch, many, many thanks. This was the better hours we've had in a long time. So we'll keep picking your brain. We know you're a busy guy, but this was super, super helpful.
Yeah, absolutely. My pleasure. It was great to meet you all. And I really think that what you're doing is very important to get the next generation of folks interested in DAC and doing real research, and keep it up. All the best, and let me know if I can be helpful in the future.
Yeah, that means a lot coming from you, Kirsch. We know you know a lot, so really appreciate it. All right, everybody. We'll see you folks next Thursday. I'll be back in New York, and hopefully, I think we'll probably have a few other people, but hopefully more people tuning in. Thanks, everybody.
Thank you.